The first time I heard about the symbolics.jl package was a few weeks ago when I was making my video on image processing. Since I didn't know anything about the package back then, I thought I'd take some time this week to learn about symbolic computation and to learn how to use the symbolics.jl package. That way, I can share what I learned with all of you. So what exactly is symbolic computation? And how can you perform it in Julia using the symbolics.jl package? Well, let's find out. Welcome to Doka.jl, where I explore the vast Julia wilderness and turn my discoveries into wholesome Julia tutorials. When solving math equations, you typically have two choices. One, you can solve problems numerically, meaning that the solution involves only numbers. Or two, you can solve the problem symbolically, meaning that an expression may be used to represent the solution. When using a computer to solve math equations, it's often done using numerical computing. Solving problems symbolically has traditionally been done by hand. But it is possible to use a computer to solve equations symbolically. When you use a computer to solve equations symbolically, that's called symbolic computation, which is also known as computer algebra. Julia is well known for its strengths in both scientific computing and in numerical computing. What may be less known, at least to me, is that Julia also supports a very fast version of symbolic computation. Within JuliaLand, the gateway to entering the world of symbolic computation is through the symbolics.jl package. Software that allows you to perform symbolic computation is known as a computer algebra system, or CAS, or CAS. There are several computer algebra systems available for free online, but the problem with them is that they're standalone systems, so you can't use them with your programming language. The symbolics.jl package is a computer algebra system written in Julia, so by using this package, you can use Julia to solve your problems both symbolically and numerically without ever having to leave Julia. And because it's written in Julia, it also happens to be very fast. Some of the code for the symbolics.jl package can trace their roots back to several different packages that provided symbolic computation as a feature. But the code has since been elevated into its own package, emerging from the Julia Lab, which is Professor Edelman's lab at MIT. The lead developers are Shashi Gowda, Yingbo Ma, and Chris Rackauckas. But it's a large project, so here's a list of all of the collaborators who authored a paper on the symbolics.jl package that was published in 2021. Currently, you can use the symbolics.jl package to solve math problems from algebra up through differential calculus. But at the moment, you can't use it to solve integral calculus problems. For that, I'm going to use another package that's still under development, named Symbolic Numeric Integration.jl. This is also a large undertaking that falls under the SciML umbrella, with the lead developer being Shahriyar Yeravanian. I apologize for my pronunciation. Here's a list of all of the collaborators who authored a pre-publication paper on the Symbolic Numeric Integration.jl package in 2022. I've provided links to both of these papers in the description below. So these are both relatively new packages, with some big Julia names attached to them. So let's check them out. Let's fire up Pluto and create a new notebook. let's start by loading a few packages. The most important step when using the symbolics.jl package is to define your symbolic variables using the @variables macro. For this demonstration, I will be defining 4 symbolic variables: t, x, y, and z. Once you do that, anytime you use the variables t, x, y, and z in this Julia session, Julia will know that these are symbolic variables and not ordinary Julia variables. The best way to get familiar with the symbolics.jl package is to look at some examples. Let's start with an example from algebra. Anytime you use symbolic variables in an expression, the symbolics.jl package will generate a symbolic expression. Here, the equal sign is the variable assignment operator, assigning the symbolic expression to the Julia variable named ex0. The tilde character is used inside of a symbolic expression for the equal sign within the symbolic expression. The symbolics.jl package will automatically display the LaTeX version of your symbolic expression in Pluto. As an FYI, Pluto uses MathJax to display your expression. So if you ever want to see the underlying text code, you can right-click over the display and select Show Math As Text Commands. In any event, note that the sequence of the displayed symbolic expression may not be the same as the expression that you typed in. In this case, I typed in x before y, but in the display, y is before x. This is your first clue that the symbolic expression is not the same as ordinary LaTeX. With ordinary LaTeX, you can't perform any calculations with it. It's literally just typesetting. But a symbolic expression is Julia code that just happens to look like LaTeX. And because the symbolic expression is Julia code, you can perform calculations with it. For example, you can take this symbolic expression and symbolically solve for x, or symbolically solve for y, simply by using the solve for function from the symbolics.jl package. These symbolic solutions are just like solutions that you would have done by hand in algebra class. Now, where symbolic computation starts to get interesting is with linear algebra. In this example, we're going to create a system of 3 symbolic linear equations, and then we're going to solve the system numerically by using the symbolics.jl package. So, given the system of linear equations, we need to find the values of x, y, and z that satisfy all 3 of these equations. A standard way to solve this problem would be to place all of the coefficients on the left-hand side of the equations into a matrix. By convention, this matrix is named uppercase A. And then, all of the values along the right-hand side of the equations would be placed into a vector. By convention, this vector is named lowercase b. And then, we would use a\b to find the values of x, y, and z. When using the symbolics.jl package, you can just use the solve for function to find the values of x, y, and z. So all 3 of these equations are satisfied when x equals 1, and when y equals -2, and when z equals -2. Pretty cool, right? Now, there's a caveat. Currently, this solve for function only works if all of the equations are linear equations. Even so, it's still very helpful to see the symbolic expressions, as opposed to seeing just a matrix of coefficients, or a vector of values. Using symbolic expressions may make the problem-solving process a little less abstract and a little more concrete. So that linear algebra example was interesting. But where symbolic computation gets really interesting is with calculus. This example is from physics, and it shows the relationship between position, velocity, and acceleration. The velocity function is the first derivative of the position function, and the acceleration function is the first derivative of the velocity function. In other words, the acceleration function is the second derivative of the position function. You can solve this problem numerically by using Julia packages like 4diff.jl or differentialequations.jl. But with symbolics.jl, you can solve this problem both symbolically and numerically. Finding the symbolic derivative using the symbolics.jl package is a two-step process. First, you need to use the differential constructor to wrap a differential operator around a symbolic expression. Then, you need to use the expand derivatives function to display the symbolic solution. So this symbolic expression is the same symbolic solution that you would have come up with if you had solved this problem by hand. You can repeat this process to find the symbolic expression or acceleration. Now, these symbolic expressions are not just pretty pictures. You can use them to solve problems numerically. Let's set up a Pluto slider so we can change the values for time. In order to replace a symbolic variable with an actual number, you need to use the substitute function. When using the substitute function, the number needs to be inserted using a dictionary. So now, you can see the position, velocity, and acceleration at any time t by moving the slider. Fun, right? For calculus, the symbolics.jl package currently only supports differential calculus. There are some other packages currently under development for symbolic integral calculus. One of those packages is called symbolic numeric integration.jl. Let's take a look at that package next. Let's create a new notebook and then load the symbolics package along with the symbolic numeric integration package. Next, let's define a symbolic variable, x. Currently, the symbolic numeric integration.jl package only works with expressions containing a single variable. This first example comes directly from the symbolic numeric integration documentation. To set up a symbolic expression to be evaluated, use the same syntax that we used for the symbolics.jl package. The symbolic numeric integration.jl package contains a single function called integrate, which will find the symbolic solution to the integral of your symbolic expression. The function returns a tuple containing 3 elements. The first element is the symbolic solution. The second element is the residual unsolved portion of the input. And the third element is the numerical error in reaching the solution. As long as the second and third elements are 0 or close to 0, you should be okay. In this example, both values are 0, but that's not always the case, so you need to pay attention to those values. To see the solution, you can index this tuple just like you can any other Julia tuple. So what's implied in the solution is that there's some constant c that needs to be added to the end of the solution. Otherwise, this solution is the same symbolic solution that you would have come up with if you had solved this integral by hand. Pretty cool, right? For our next example, let's revisit the example that I used in episode 807, which covered numerical integration using the quadgk.jl package. The function that I used in that episode was the square root of x. Just like before, all we need to do is use the integrate function to find the symbolic solution for the integral of the square root of x. And that's it. Simple, right? Now the solution is just a symbolic expression. As we saw in the previous notebook, we can plug in numbers into the symbolic expression by using the substitute function along with a dictionary containing the number. But the symbolics.jl package provides you with another way for you to interact with these symbolic expressions. You can actually convert these symbolic expressions into Julia code that you can use just like any other Julia function. There are a few steps involved, but the workflow is pretty straightforward. The first step is to assign the symbolic expression to a variable. The next step is to use the build function to generate an intermediate representation of the function. This code is the intermediate representation of a function which takes the argument x and returns the result of this calculation. Then the next step is to evaluate this intermediate representation. Now, you can use this just like any other Julia function. So for the function, the square root of x, the area under the curve and above the x-axis when x is between 0 and 4 is 5.33 repeating. Let's take a moment to appreciate just how clever this is. Knowing that this workflow exists means that you can now solve problems symbolically on your computer, just like you learned how to do manually in school. And then, you can take your symbolic solution that's in the form of a Julia symbolic expression, and then convert it into a Julia function. Once your solution is in the form of a Julia function, then you can do whatever you want with it, with any package in the Julia ecosystem. Thus, blurring the line between symbolic computation and numerical computing. Now, I have to caution you that both of these packages are still under development. so it's imperative that you check your results. One of the exciting things about using Julia is that you get to witness the birth of a new language in real time. But as with any research and development environment, you need to be aware of the experimental nature of those activities. Now, that's a lot to think about, so let's break here, and I'll share some of my final thoughts. It's not clear to me who currently uses computer algebra systems. If you currently use a different computer algebra system, let me know in the comments below. How are you using it? Not only would it be helpful for me, but it would also benefit anyone else who may be watching this video. After spending a little time with it, I can see how using a computer algebra system might be useful for teaching purposes. I can also see how it might be useful for transitioning from the theoretical world of the classroom to the applied world of research labs. I can also see how it might benefit those who are looking for an alternative way of solving a problem in order to enhance their understanding of either a manual symbolic solution or a numerical computing solution, or both. One of the nice things about using Julia is that Julia is agnostic. Do you prefer symbolic computation? No problem. Do you prefer numerical computing? No problem. Do you want to use both at the same time and switch back and forth between the two? No problem. Julia's got you covered. Now that I have some experience using the symbolics.jl package and the symbolic numeric integration.jl package, I think that both of these packages are pretty cool and fun to use. If you enjoy using these packages, please consider going to their respective GitHub pages, and please consider leaving each of them a star. By uploading this video, I have reached a channel milestone that I'd like to share with you. This episode, episode 809, is my 100th episode. When I started learning Julia a few years ago, I couldn't imagine that there was enough content to fill 100 episodes. But here we are. I'd like to thank all of you for watching, because without you, there wouldn't be a channel. I'd especially like to thank all of my channel members and channel donors. I know that times have been tough for everyone during the past few years, and this year is especially tough. I know that I'll never be able to repay you, but I want to let you know that your donations keep me motivated to keep producing educational materials for the entire community. Thank you to all of you for joining me on this journey. With that said, there's still a lot more material to cover, so stay tuned for more wholesome episodes.